All right. So now we want to do an example of where we actually use this first derivative test, just to see it in action. All right. But I wanted to have it up here again, just so you can remember what it is that we're trying to do. Right. So there's a certain process we need to do. We first need to find all of the critical numbers, and then we want to check the sign of the derivative basically between all of the critical numbers. So imagine we take a number line and we put all of the critical numbers on it. Okay? Then, in each of the chunks that those critical numbers cut it up into, we're going to test the sign of the derivative there. Right? So, how is that going to look? So, let's start by finding the critical numbers. Step 1. Critical numbers. Right? And remember, the way we do this is we take the derivative and set it equal to 0. So the derivative here, let's see, we get 12x cubed minus 12x squared minus 24x. Okay? And if we're trying to set this equal to 0, we want to solve that. And so the best thing to do is probably, let's start by factoring out 12x. Get x squared minus x minus 2. And if we factor this some more, 12x, x minus 2, x plus 1. Right? So, what are our critical numbers here? Well, we have 0, 2, and 1. Right? So we have our critical numbers. Now, here's what we're going to do. So step 2, I'm going to call this classify. Right? Classify them. Not then, them. Right? So the way I like to think about this is I want to draw a number line here. Let's put 0 here, put -1 over here, and let's put 2 over here. All right, this is obviously very much not to scale, but that's fine. Okay? So here's the x values. Up here, what I want to do is we're going to write down the sign of the derivative. Right? Now we know at each of these critical numbers, the derivative is 0. We know that because, well, that's how we found it, right? That's how we found the critical number. So what we need to do is in each of these gaps here that we have between these zeros, so all 4 of these gaps, we want to look at the sign of the derivative. Okay? So what I like to do here is say, well, we're just going to take some test numbers. All right. So over here, I'm going to take -2 as a test. In here, we need something between -1 and 0, so we're just going to have to deal with -0.5. Okay? In here, we have 0 to 2, so we can pick 1. And in here, we can pick 3. So now, we can test whether f prime is positive or negative. And all we have to do is check it at these numbers because we know it's not going to change sign in the middle here. It has to stay the same throughout. Right? So what we're going to do with this is plug these numbers into the function, into the derivative. Now here's the thing though. We don't need to know the actual value of the derivative. All we need to know is whether it's positive or negative. So, right? So f prime, we know that f prime of x is 12x, x minus 2, x plus 1, right? We factored it earlier, right, up here. Okay? Now, what's really great here about this is, since we're only interested in the sign, we can just look at the sign of these three components individually. Okay? So, it can help to sort of make a chart for this if you want. So we have to test these 4 x values. I guess I'll just go to the next page here. So I'll call this test value. All right, there's 3 factors here. 12x, x minus 2, x plus 1, and then f prime of it. Okay, so here we have -2, -1/2. That's 1 and 3. Okay. Now what we're going to do is we're just going to look at, if we plug this number in here, is it positive or negative? If I plug in -2 to 12x, I get a negative number. If I plug it into x minus 2, I also get a negative number. If I plug it into x plus 1, I also get a negative number. So over here for f prime, negative times negative times negative is a negative number, right? So the derivative here in this segment is all negative. Okay? Now if we go to the next number, 1/2, or -1/2, if I plug it in here, it's negative. -1/2, if I plug it in here, is also negative. But if I plug it in here, it's positive. Negative times positive, a positive number. So that means in this next segment here, from -1 to 0, all positive. All right. Let's do this for 1. All right, if we plug in x equals 1 here, positive. Plug in x equals 1 here, it's negative. Plug in x equals 1 here, we get another positive. Positive times positive, that's negative. So these are all negative. And then finally, we're going to do this with 3. Plug 3 in here, we get a positive number. Plug 3 in here, also get a positive number, and here as well. And so multiplying 3 positive numbers gives you a positive number. So all positives. Right? So let's duplicate this down here just so we can look at it more easily. Let's use our first derivative test knowledge now to classify these points. All right, so here we went from negative to positive. So this one right here would be a local minimum, right? Because we're going down at first and then back up. Here we're going positive, then we switch to negative. This is a local max. And here, this is a local minimum. All right? So how do we really want to kind of summarize this? All right? Best way to kind of summarize these points here, we'll say f has so I guess one thing I want to point out is the difference between a local minimum and a local minimum value. The local minimum or local maximum happen at these x values, -1, 0, and 2. The local minimum value or local maximum value is plugging this into the function. Okay? So we'll just say here, to keep life a little simple here, actually, we'll plug in the values. So I'll just tell you what they are. So here, F has a local minimum value of f of -1, which is 0, at x equals -1. Okay. A local maximum value of f of 0, which is 4, 5. 5 at x equals 0, and another local minimum value of f of 2, which is -27 at x equals 2. All right. So we've classified -1, 0, and 2. Right? X equals -1, x equals 2 are where the local minimums occur. And then if we plug those numbers into the function, we get the local minimum values. Right? And then x equals 0, we found we had a local maximum. And if we actually plug that into the function, we get the local maximum value, 5. Right? Hope that example helped out and clarify what this is about. And we'll see you for the next one.